So the first lecture really is why JEDI? Why are we doing all this and starting a new data assimilation system? So first of all, the Joint Center for Satellite Data Assimilation, JCSDA, we are a multi-agency center that's, and the goal of JCSDA is to improve the use of satellite data for analyzing and predicting the weather, the ocean, the climate, and the environment. We are a collaborative organization, and we are funded by the Weather Service, NESDIS, OER, which are 3 branches of NOAA, by NASA, GMAO, the US Navy, and the US Air Force. And we have a few additional partners as well with whom we are collaborating. And the JCSDA is organized by project. I've mentioned a few projects here. One that probably a lot of you know is a CRTM, Community Radiative Transfer Model. JEDI is the main data assimilation project, so the joint effort for data assimilation integration. That's why you're all here. And we have a few other projects that are kind of connected to all that. So the SOCA, which is the CI solution coupled assimilation. We have an OBS project, which is really looking at all the scientific aspects of how to improve the use of observations. And we have a land project that's a little bit more recent than the others, but looking at land surface data assimilation. And so these projects are living, and we can add projects as we go. You know, some projects might at some point be complete and others will start up. So that's hopefully a dynamic structure. Really, so the mission of the JCSDA has been evolving a little bit in the past 20 years. So the JCSDA started around the year 2000, and the goal at that point was really to include new observations into CRTM, mostly with new sensors that were coming in the early 2000s. Then in the 2010s, the focus was mostly on using all sky, all surface radiances, and hybrid DA techniques, these kind of things. And in the 2020s, really the focus most likely is going to be on coupled DA of various kinds, and that's where the JEDI project really comes in. But the goal of a JCSDA really throughout the decades like that has always been to improve, and will continue to improve the use of all the data that we get, mostly from satellites. And we're just kind of, as the time goes on, we're just addressing the new challenges that come with the new data and the progresses in science, in data assimilation science. So within the JCSDA, the JEDI project, sorry, the list of contributors here is not, it's the one from last year. It's not the one from this year. I should have updated that. The main point here is that the list is fairly long, and we keep having new collaborators, you know, almost every week. So it's a fairly big project that's centered around the core team at the JCSDA. But we also have partners from NOAA, EMC, NOAA, Israel and Boulder, from GMAO, from NCAR, from the UK Met Office, from the Navy. And again, hopefully that list will grow over time. So it's definitely something very collaborative, and that's also why you're here, to learn about the system and to keep it, to open it even to more collaborations. So this is the joint effort aspect. All right, so sorry, I'm having trouble with my PowerPoint. idea of the JEDI project was to reduce the duplication of effort between the JCSDA. In traditional data assimilation systems, when new observing systems come online, it takes a lot of effort to add them to a data assimilation system. And that effort is typically duplicated in all the partner agencies of a joint center. So what we want to do here is to reduce that effort so that if one center puts in a new observation into the system, then other partners can also use it. That's a big driver behind the JEDI effort. And this is also true for new data assimilation algorithms. We want a system where any algorithms, any algorithmic development that's put in by one of the partners can be used by other partners. So the first part about the observation is really addressed by the UFO and UODA components part of the JEDI, and the second part is really the OOPS component. Another aspect, as I mentioned earlier, one of the challenges going ahead is going to be the coupled data assimilation. So we also want to have a system that works for all components of the Earth system. So that's why we're developing data assimilation in JEDI for the atmosphere, but also for the ocean, sea ice, the land. And once everything is in the same system, we can move towards really coupled data assimilation development, so there's a lot of new science to be done. Also, everything we're developing in JEDI is for research and operations. So that research and operations have slightly different constraints in terms of how they view code and a data assimilation system, and we're trying to integrate both constraints into the system, and hopefully that would be really usable by everybody. So the approach is that modern data assimilation systems really are too complex for one person to know in its entirety. So we need to collaborate, and we need what's called separation of concern, so that somebody or a group of people can work on one aspect of a problem without breaking everything else and pieces that are unrelated to the area they're focusing on, which has been a major difficulty in traditional codes, where very often somebody changes something and it breaks in all kinds of ways that are unexpected and in parts of the code that are unrelated. So we're trying to move away from that. And we also, so what the main driver behind that, we want to modernize use modern software practices in order to achieve this goal. You all see around you that software has evolved a lot since the last 20 years. You see that software you use on your phone, they have releases every week, and development is very, very quick. So we want to take advantage of all these technologies that have come up for improving the speed of development, also make the maintenance a lot easier, and this increase the portability and the efficiency of all the software we're writing. So we're not developing on one machine and assuming it will always run on that one machine. So the main, well, at least the first component you will see in JEDI is what is called OOPS, the Object-Oriented Prediction System, which is a project we had started at ECMWF quite a few years ago now. The idea is that of OOPS is that there are a few high-level blocks that are used in every data assimilation system. So typically, when you read a paper about data assimilation, you read about states, you read about the model, you read about covariances, observation operators, and a few other things. And your papers, they describe equations, they describe a data assimilation algorithm using these entities. They don't really tell you how these things are implemented, and that should reflect in the code. So we have an abstract layer, which is this blue box here that has these elements that are in green here, and all the data assimilation algorithms on the top are written in an abstract way using these green boxes. And that's the OOPS system. And then underneath, somebody state what's a model, what's a covariance for a specific system. But we clearly separate the two aspects here with that green layer of interfaces, which you will hear more about. And in addition to that, so the JEDI project is adding a few layers to that. So we have the abstract layer at the top, and with generic data assimilation algorithms that are in blue, that are based on these green boxes. And in JEDI, we are also writing some of the implementation of some of the green boxes in a way that's generic. So for example, we have a Saber component, which is a system agnostic background error representation that's implementing a number of B matrices that can be used by any model. And it's the same for the UFO, the unified forward operator, where we're developing observation operators that can be used by any model. So we are adding more genericity, more generic components to just the OOPS layer, which was really focusing on the data assimilation algorithms. So you will hear more about that. And the idea there is that these generic components can be shared between the partners. So if somebody adds a new formulation for a background error covariance matrix, or if somebody adds a new observation operator, it can be shared and used by the other models as well, which is something fairly new. So model interfaces. Just going to go very quickly here. Basically, the way JEDI sees a model is that we see as each model as a create and initialize steps. That's something happening at the beginning. Then there's a loop over time, and there's a step method that's doing whatever is needed in the time step. And then there is at the end a finalize and a destructor for the model object. We don't go any deeper in the model, and we don't want to go any deeper. Even the step is up to the model to really define, what's a step. And all we care about really in the data assimilation and in the JEDI world is some kind of time resolution that the model will have, and that we can advance the state by a certain amount of time. But how it's done inside, we don't see that in JEDI or in OOPS. The reason we went to that level and we stopped at that level is that we want to be able to add between the time steps some computations that are specific to the data assimilation. So that's typically the observation operator, but that can be also other things like a digital filter or various other aspects that we want to handle in the data assimilation. So really the idea of this model interface is to separate, again, separation of concern between people developing the model should be able to do anything they want in the model, and that should not break the data assimilation and vice versa. So we will see more details about that as we go. So this is just to give you an idea of the number of models that are interfaced already with JEDI, and this list keeps growing. So we can see we have a number of atmospheric models, but we also have ocean models, sea ice models, and some toy models that will be used for, they'll be very nice for learning the system, for education purposes, for testing new data assimilation algorithms. And for debugging, typically when we develop something new, we test it with these toy models before going to the real models, because it runs a lot faster and it's a lot easier to do the initial debugging. It doesn't mean that it's enough. You still have after that to run with the real models, but it's a nice step that if you develop with a traditional data assimilation system, you don't have that flexibility of testing with a simple model first. If you test an algorithm with a Lorentz model, you have to recode it completely when you move to a real model. Here, it's not the case. You code it once and you can test with a toy model and then go to a full-blown model without changing a line of code, hopefully. Then we have observation interfaces. So here it's the UFO that I mentioned before. The idea is to share observation operators between JCSDA partners and reduce the duplication of work. So we are taking the model agnostic approach here, one level down into the observation operator. The driver behind that is to make faster use of new observing platforms. There's a number of reasons for that. Regular satellite missions are expensive, and if you think of a satellite being in orbit for a year before you can use it, that's typically the cost of keeping a satellite in orbit for a year is in the hundreds of millions of dollars. So if it takes you 1 year to start using it, it's hundreds of millions of dollars that have been wasted because the data has not been used for that initial year. We also see more and more CubeSats that are coming up, and they are expected to have a fairly short lifetime. So if you can't use them quickly, then they have no use to you. So we need, this fast pace of development for the forward operator. And hopefully also we can convince more users and instrument science teams to develop in this UFO framework, because if they put their effort there, they know that it will be used by all the operational centers that are part of the JEDI JCSDA community, and that gives extra incentive for people to make sure that their instruments are available there, because that's reaching a lot of users without to have to re-implement the operator for all kinds of different data assimilation systems. So the idea really is that these forward operators would be like an app store where you can go and pick whatever from a whole collection of observation operators which you want to use. How we're doing that? I've tried to make a picture here of a traditional data assimilation system where the observation operators, they're accessing data in the state, accessing data in the observations, and there's no clear boundary. It's all very fuzzy. And as a result, it's all very specific to a given data assimilation system and a given model. And that's absolutely not shareable between different models and different data assimilation systems. So what we do in the UFO is that we've added a layer of interfaces. Again, that's still this idea of separation of concerns between the state and the ops operator. So we can, the ops operator knows the observation locations and needs as input, so we can pass that into the state that will return the field values for these variables at these locations to the operator, and then can do its job. So hopefully that uniform interface will make it possible to share the observation operators. As long as this interface is respected, then you can see that the state on the left here could be completely different, as long as it has this method that can give the values at the relevant locations, then the observation operator can be the same. We also have this idea of filters, so that's mostly for quality control, that can be called just before or just after the observation operator itself. I'm not going to go into the detail here. We'll go back into that throughout the week, but again, the idea is that these filters are generic. So for example, background check is written once and can be applied to any observation type with exactly the same code, and you don't have to rewrite it for every single observation type, which is a nice feature, and it's entirely controlled from YAML configuration files. So it's a very, very flexible system. And again, it saves a lot of recoding because you can reuse, if you have a new observation, you can reuse the same filters, just maybe change your thresholds or a few parameters in the YAML file, but the code is the same. Observation handling, that's also another aspect we're looking into. In typical systems, there are many observations files of many different formats, and this is very, very difficult to maintain, very difficult to exchange information between different centers, because all these intermediate files typically have different formats between the centers. And it's also, as we're thinking about the future, where we would like to move towards more continuous assimilation of observations, for example, It's very difficult to implement in a system like that, with the steps are too distinct from each other, and the observation files are too different at every step to really merge all that together. So we are moving towards interface for accessing. So that's what we call the YODA here, the interface for observation data access. And when data arrives, we decode it, we put it under that interface, and then everything, the pre-processing, post-processing, data assimilation, all work for that interface. That gives us a lot more flexibility, and it's also a lot more shareable between different people. Hopefully that will hide the memory hierarchy between disk, archive, and, in memory and all that. That's a long-term goal. But that's also one area where we're trying to put more in common so we can share more between the centers. So working practices. As I mentioned at the beginning, there are many people involved in this project, many organizations, many models, and still we are making fairly fast progress. We started this project from a blank sheet about 3 years ago, and we have now issued our first release of the code. So we've worked fairly fast if you think of the time it takes to develop operational systems. It usually takes much longer than that. And for that, we've adopted new ways of working. First, the project methodology is inspired by Agile and Scrum. So we have to adapt it a little bit because we have a distributed team and we have many people who are part-time. So we had to adapt a little bit the typical Agile methodology that really calls for, it usually works for fairly small teams where you have a physical meeting in the morning, every morning, and we couldn't do that. But the idea still is to work in small, manageable increments and with constant feedback and constant discussion, so we can continually improve the way we work and the way the code is working. So we have a very collaborative environment. All our source code is in GitHub. We're using ZHub for discussing, exchanging information. There's a lot of pull requests and code reviews where we are really encouraging everybody to be actively involved. We have very regular meetings, some involving the whole project, some by sub topics within the project by video. We also organize code sprints, at least we were before this current crisis, where we had 8 or 10 people working in the same room for, let's say, a week on a very specific topics with very specific goal, and working very hard for a week together. So we are moving that also to a more remote type of code sprints at the moment. But hopefully we'll have more code sprints in the future. But that's really nice, a nice way to get work done, to really focus on something for a week and kind of ignore emails and meetings and just spend 1 week focusing on something. It's also a good way for people to meet each other and know each other. And typically people who've met in code sprints, we keep working together after the code sprints. So that's also a very nice way to increase collaborations between the different centers that are part of the JCSDA. So all that really relies on modern programming technologies like object-oriented programming and generic programming. We'll talk about that a little bit more. So the code is organized in many repositories. So that's, there's the OOPS, that's the main data assimilation algorithm that's relying on Saber for the background layer covariance, on UFO for the observation operators, which itself uses the CRTM, and YODA for handling observation data. And then on the left, we have all the models that are interfaced with JEDI and OOPS. And this all works together. Really, the idea here is separation of concern. Each aspect of the problem is handled by a piece or a repository that has the code that corresponds to it. And we don't want a gigantic monolithic enormous piece of code that nobody really understands. And so it's a lot more modular, but in the proper sense of modular, not in the Fortran sense of modules. And it's a lot easier to work with when you're specializing into background error covariance. You can focus on Saber and not worry too much about the rest. And if you're a CRTM specialist, you can work on CRTM and not have to worry too much about the rest, etc. Together with this new ways of working, we have some tools to enforce software quality, so making sure the code is correct. So there's a lot of tests and coding norms, a lot of tools for automating the tests, because it's not of much use if you have tests and you don't run them automatically. Every time there is a change in the code to make sure nothing is broken. There is an effort on portability, where the tests are systematically run with several compilers, with 3 compilers at the moment, but it'd be nice to have even more. And we also have versions of the code in containers that you will see this week. And there is a big effort also on documentation, which I hope you will find useful. And the documentation is the rest of the code. It's in repositories that everybody can edit and issue pull requests for documentation to improve it continuously. So JEDI academies, we had some physical ones in the past. We now have a virtual one, so it will be more difficult to do a group picture at the end, but hopefully that will be just as useful and productive as the physical JEDI academies we had in the past. And again, just a picture of what code sprints used to look like. It's really people sitting together with computers and doing some coding and discussing as the coding gets done. It's not a code sprint is not a workshop, or it's not about discussing or having presentations. It's really about coding, and that has been super useful when we started the project, and I hope it will continue to be. All right, so final comments. We are hoping that JEDI is going to trigger long-term collaborations, and there are a number of things we need to do for that. We need to have code reviews, and we need to be fairly quick when people want to make a change. We need to be proactive in reviewing the code, discussing it, and merging it, or asking for modifications if they're needed. The fact that code has been merged doesn't mean that it's used in operations. Each operational center still has a choice how they want to configure the system, and they can activate or not all the options that are in JEDI. JEDI has a whole bunch of data assimilation algorithms, and each center will choose which one you want to use, which observations we want to use, etc. So just because the code is in doesn't mean it's in operation. It just means that we put code in when we estimate that it's useful enough for the community to have it in the system. And there's a number of steps there, from technical development and there's scientific evaluation, move to operations. And the idea is that all these steps, there's constant feedback. So it's based on the agile practice where every development is constantly being discussed and improved as we go. So there is a long-term plan, but there is also room for short-term changes and improvements as we go. It's not all cast in stone 5 years ahead of time. And the idea is that things stay relevant. The environment in which we're doing the project is constantly changing, so we need to adapt to that. There's no point having a project that would be planned 5 years ahead, and by the time it's finished, it has become completely irrelevant because the environment has changed, or the conditions around it have changed, and the project has become obsolete before it's even finished. So we're constantly evolving. I think that's my last slide. So we are bringing all this, this software development technologies and working practices to the community. We've had a release in October, and this is definitely a different way of working from what most of you know. And it's challenging for everybody. You know, when we are all used to a certain way of working, we have to change our habits, and that takes time. That takes discussion, that takes curiosity, which I hope you all have if you're part of this academy. But we are not really inventing, you know, if I can reassure you, all these technologies, software industry, we're not inventing something easy out of a hat. It's really things that software engineers use every day in the industry around us. And if you look at, you know, what you can do with a smartphone nowadays, I think the software industry really has shown that it can work. So yeah, I think I've said the rest already. We want to share as much technical infrastructure as possible and reuse the various components that are part of a data assimilation where and when it makes sense. But each partner and each application really keeps control of what elements of the system they want to use and how they want to configure it. And really the keys to that are the separation of concerns, which you will hear quite a lot about this week, and the interfaces between these different elements so that they work well together. So I will stop here. Thank you for listening, and can go to the questions.